Okay, so now we've talked about vector spaces and given some examples of vector spaces. Now we want to investigate some vector space properties. Vector space properties are statements that are true for any vector space. So what we're going to show in this section, they're true for all of the examples of vector spaces that we've seen so far. They're true for polynomials, they're true for infinite sequences, they're true for column vectors, they're true for matrices, they're true for functions, they're true for any mathematical structure that satisfies all the conditions that a vector space has to satisfy. Okay, so this is very powerful. What we're going to show here holds for many, many different specific examples. This shows the power of mathematical abstraction to be able to prove a great deal from some general principles. Okay, so here's our first principle. We're going to show that there's just one zero vector. There can't be more than one zero vector. Remember, the zero vector is a vector such that 0 plus any other vector is equal to that vector plus 0, which is equal to that vector. That defines a zero vector. Now, on the face of it, there might be several zero vectors. You can't tell. You need to prove that there is actually only one zero vector. So for matrices, for functions, for infinite sequences, there can be only one zero vector. So that's this theorem here. The zero vector is unique. There's only one in any particular vector space. Now that isn't to say that the zero vector in the column vectors is the same as the zero vector in the matrices. It says if you're given a vector space, in that particular vector space, there's only one zero vector. Okay? So here, let's suppose, to prove this, let's suppose that we have two objects which are zero vectors. And we're going to show that these two objects must actually be the same object. So these are just labels. And we'll have to show that these two things must label the same thing. Okay, so these are both zero vectors. They both satisfy the properties of zeros vectors. Okay. Now, according to the property of that 0, 2 is a zero vector, we know that 0, 1 equals 0, 1 plus 0, 2. That's because 0, 2 is a zero vector. Now we have additive commutivity, so we can exchange the order. That's the same as 0, 2 plus 0, 1. Now we know that 0, 1 is a zero vector. We know 0, 2 plus 0, 1 is equal to 0, 2. So what's our result? We've shown that 0, 1 is equal to 0, 2. So any vector that is a zero vector must in fact agree with any other vector that's a zero vector, which means there's only one zero vector in any particular vector space. Okay? Similar idea is the idea that additive inverses are unique. Could there possibly be, we know what additive inverse means, that u minus, or let me just call let's call the additive inverse minus u. U plus minus u is equal to minus u plus u is equal to the zero vector. Now, is it possible that if I have one vector, is it possible that there are two different minus u's? Okay, so that's what we're going to see now. We're going to use the very same technique. Suppose minus u1 and minus u2 are two different, or I'm sorry, are two additive inverse for u. We're not going to assume whether they're different or not. We're just going to say these are both labels for additive inverses for u. And we're going to see that these are actually must be the very same vector. Very similar proof here. Let's start off with minus u1. Now we know we can add 0 to that. And we know that u plus minus u2 is equal to 0 because minus u2 is an inverse of u. So we can replace this 0 with u plus minus u2. Now we can reassociate and also use commutative property. This should be plus commutative property also because no, I'm sorry, I didn't use commutative property yet. Okay. They just reassociated so that minus u1 and u go together. Okay. Then here we'd actually need to use commutative property to show that this is 0 also. So this is minus u1 plus u. I'm sorry, I don't think you do need commutative property because it's when it's defined it goes both ways. So my mistake, everything here is fine. Okay. We have the additive inverse property allows you to get 0 here, so you have minus u2. So you kind of have a bait and switch here. We added 0, wrote 0 in a different way, reassociated, and then found out that the other minus u is the same as the original minus u. Okay? All right. So far we've been proving facts about zero vectors, additive inverse vectors. Let's prove something about scalars. All right, so we'll prove something about the zero scalar in scalar multiplication, that the zero scalar times any vector must be the zero vector. Now for column vectors, this is pretty clear, but what we're going to show here is that no matter what space, what mathematical object satisfies vector space properties, this will always be true. Okay, a very similar type of proof. So let's start out with 0 times the vector, and let's add 0 to it. And we're going to write 0 in a different way, and we'll show that this still works. Okay, so let's write 0. We'll write it as the additive inverse of 0u plus 0u, and that's going to be equal to the 0 vector by the property of additive inverse. Okay. Okay, so let's reassociate. We can reassociate and write 0u plus 0u together. Okay, and then we use multiplicative distributivity of multiplication by scalars. Okay, so here we have minus 0u plus 0u, and that turns out to be 0. Now this does seem kind of like a rabbit out of the hat. To know how to construct such proofs needs some experience, but at least you can follow along this proof and see that this 0 scalar times any vector will be equal to the 0 vector. Okay. On the other hand, if we have a scalar times the 0 vector, we will always get the 0 vector. You can read through this proof, very, very similar type of argument. Okay. Okay. All right, now let's look for additive inverses from scalar multiplication. Now we see from this notation that the additive inverse of u looks like minus 1 times u. We need to justify that notation. We haven't proven that if you take the scalar minus 1 and multiply it by a vector, that gives me the additive inverse of the vector. All right, and you can read through this very, very similar type of proof. You're adding 0, writing 0 in a different way. You're going to break it up, reassociate, and find out that minus u can be written as minus 1 times u. Okay, so this shows that this notation works, that if we have 6u1 plus the constant minus 4 times u2, that's the same thing as 6u1 plus the additive inverse of 4u2. Okay, so this looks like a vector subtraction. Vector subtraction should be understood as 6u1. Here should be 6u1 plus minus 4u2. I should write this. Sorry, let me do that again. 6u1 plus the additive inverse of 4u2. And that's what that means. Now we know that the additive inverse of 4u2 can just be written this way. So there's no ambiguity in this notation. All right, now this next theorem is reminiscent of a fact that we know from ordinary arithmetic. If you take two numbers and you multiply them together to get 0, then either one is 0 or the other is 0. We know that from real numbers. We know that from integers. It's also true for complex numbers. The only way to get the product of two numbers equal to 0 is if one or the other factor is 0. Okay, and this is a very important property when you're dealing with polynomials. So we're going to show something similar holds for vector spaces. Okay, so if you have, here's the theorem. Suppose that V is a vector space and A is a scalar in the complex numbers. If alpha times u is equal to 0, now of course u is a vector in the vector space. So if you have any constant times any vector in the vector space and the result is 0, then either the constant is 0 or the vector is 0. Okay. And if you think about how you would prove this in ordinary arithmetic, we're going to do kind of a similar proof. In this case, if you wanted to show that u was 0, for instance, you'd multiply both sides by 1 over a. Okay, of course, you can't multiply by 1 over a if a is 0. So we're going to do the very same thing here. Okay, so there's actually two cases. The first case is that a, or I said a, it should be alpha. Suppose that alpha is equal to 0. Okay, all right, now, so you have to understand that when we're doing these cases, we're given that alpha u is equal to 0. So that's a given before we examine these cases, because that's our if. our if is something that we suppose in the proof of the theorem. So we're assuming this condition is satisfied. AU is equal to 0. All right. So two cases. If A is equal to 0, then we're done because that was the first conclusion. Okay. So if A is equal to 0, the first condition holds. We don't need to go any further. Okay. Now for case 2, we suppose that A is not equal to 0. That means that we have to show the second condition holds, because if the first condition doesn't hold, then the second condition must hold. Okay. Now if A is not equal to 0, it does have a multiplicative inverse. So I can write U as 1 times U, and I can also write 1 times U as the multiplicative inverse of A times A. I can reassociate. I can write, I know that AU is equal to 0, that's my supposition. And I have 1 over A times 0, and that's equal to the 0 vector, because we show that any constant times a 0 vector is a 0 vector. So now we have this idea. If we have a multiple of a vector is equal to 0, then either the vector is 0 or the multiple is 0. Okay. Now, this example shows that even when you have a vector space where the 0 vector looks very unfamiliar, as long as that 0 vector and all the other vectors satisfy the properties of vector space, we still get these results. For instance, in this so-called crazy vector space, the 0 vector is actually equal to this pair minus 1 minus 1. But it's still true that 0 times any vector is going to be equal to this crazy 0 vector. Okay, so as long as you have something that satisfies the vector space axioms, you don't need to worry what the objects look like. All these properties will be satisfied. Okay, we'll stop here and go on with the next video. All right, let me just add on a short commentary for this small section here. That here the author points out that we have already seen manifestations of this vector space phenomenon, that we have definitions for column vectors and definitions for matrices that are very similar. For instance, this we talked about linear combinations of vectors. This had linear combinations of matrices. This was the span of a set of column vectors. This was the span of a set of matrices. I'm not sure what this one is. Let's see what it is. All right, this one was the relation of linear dependence for column vectors. We'd had similar relation of linear dependence for matrices. Okay, you have right here. Okay, so all of these work in general. We have linear dependence, linear independence. We're going to see the same things that we saw for column vectors in a new context. And in a sense, it's nothing new, but you have to kind of enlarge your scope and understand that these apply not just to column vectors, but to any objects that can be called vectors.